All right, in the last video, I was finishing up with this slide right here. So color is not a good indication of what mineral you're talking about. You can have multiple minerals with I'm sorry, the same mineral with multiple colors. For example, quartz. Quartz comes in all sorts of different colors. It's due to certain little impurities, like some quartz will have titanium, some of them have um, like potassium or something like that, and it changes the colors. All right, and then the last thing on this list, all right, so the hardness scale is called the Mohs scale. We'll get into that a little bit. Cleavage is when the when the mineral breaks along. Usually it's some flat region where the bonds between the molecules are weakest. When the bonds for a particular mineral are exactly pretty much the same, then that mineral will undergo what's called fracture, right? And we learned that, like, for example, glass will undergo conchoidal fracture. All right, so color, again, not a good one, but not a good indicator of what mineral you're talking about. We're again, there's a lab. If you haven't done it already, you're going to do the lab on mineral identification, and then density. Density is very important. So let's look at that for a minute. Density is given the symbol rho in general in the sciences, not just earth science, in physics and chemistry and astronomy. Anyhow, the mass. This is the formula right here. Rho is m divided by v, where m is the mass. The mass. I mean, you don't. So here, let me. You like the things that we're doing in our particular textbook. The mass is in grams, and the volume is in cubic centimeters. All right. So, like, for example, a very typical density is the density of fresh water, right? Not salt water, because salt water is slightly more dense, but in grams per cubic centimeter, which, by the way, grams per cubic centimeter is the same as grams per milliliter. A cubic centimeter and a milliliter are the same three-dimensional space. All right. Anyhow, yeah, for the density of liquid water, liquid fresh water, the density is one gram per cubic centimeter. And usually we compare the densities of other things. You know, you pick up the average rock, it has a density around 3 grams per cubic centimeter, sometimes less. If it has a lot of metal in it, it's going to be more dense. So basically, the idea is, if you have something that is roughly the same size, two objects, let's say, that are roughly the same size, two rocks or two minerals that are about the same size. In other words, they take up the same volume, but one is heavier than the other. Then the heavier one has a higher density, right? Because it has more mass, of course. All right, so that's an important consideration when you're looking at minerals and of course rocks, which, again, rocks are made of minerals, right? So don't forget that, and don't forget the conditions under which something can be considered a mineral, right? You got to think about that for just a minute. All right, so let's dive into this idea of crystallization a little bit further. Crystallization is the formation and the growth of solids from a liquid or a gas. For the purposes of what we're pretty much talking about, of course, we're talking about magma, liquid rock solidifying into crystals. All right. One thing to note is inside of the Earth, the crystals are rarely allowed to just simply grow. They're usually in a very confined space. So keep that in mind when we talk about crystallization and mineral formation. That the minerals are not formed in a in an open environment. They're always being crushed by the rocks around them or the other minerals around them. All right. So anyhow, let's look at this. So atoms come together in a specific chemical composition and a geometric arrangement. Right. That's part of what makes it a crystal. The combination of the chemical composition and the arrangement of atoms in the internal structure makes the mineral unique, like quartz, for example. Quartz is unique, although it can have various various colors depending on little impurities and stuff like that. Many minerals are identifiable by their crystal form. All right, so we're going to look into that. Of course, there are combinations of here, let me see if this is in the next one. All right, so even if I cover it again, that's perfectly fine. So for example, a very typical mineral that's made out of carbon, is just carbon, is graphite, right? Graphite is like what you generally call the lead in your pencil is graphite. So this is a loose. It's a very loose connection, loosely organized molecules, loosely bonded form of carbon. It's a mineral made of carbon, and yet there's another one that has exactly the same atoms, but a different internal structure. And that, of course, is diamond, right? The hardest substance known, right? The hardest naturally occurring substance that we know of. And it's, again, made of the exact same thing that graphite is. It's just the different structure. Okay, and we'll see that in just a second. Crystal form, the shape is the outward expression of the mineral's internal arrangement of the atoms. And I showed you some of that before. There's cubic. There's different ones. Cubic. There's tetrahedral. If it has four sides that kind of form a triangle in 3 dimensions, and then rhombic, rhombohedral, I think it's called. All right. Anyhow, internal atomic arrangements are determined by the atoms. The ionic, the size of them, the amount of charge that's there, and how much the particular atoms are being packed, right? If you're talking about something that is, several kilometers underneath the ground, where the magma cooled, compared to magma that's cooling right at the surface of the Earth, the packing is going to be very, very different. All right, so just keep that in mind. Don't forget, that's actually really important. The idea of how the atoms are packed. All right, so the conditions, as I mentioned before, most crystals start to grow in a very confined region, and the big thing is the two biggest. Well, I guess it's these 3 things. Really, is that affect what crystals are going to form, what minerals, in other words, are temperature. So these are different conditions. What is the temperature? What's the pressure? And what is how much space is there for the crystal to grow? And those 3 things, and of course, what atoms are around, of course. Those things affect what crystals you're going to have. All right. So well-formed minerals are rare in nature. We really don't find them that often. Most minerals grow, as I've been saying, in very as it says, cramped, confined spaces. This is the thing I was talking about. There's graphite. Notice it's all carbon atoms, but they're loosely connected to each other. And in fact, when you do a streak, like if you get graphite and you rub it against like a piece of paper, it leaves a trail, right? That's why we can write with pencils. Diamond, however, is the hardest substance, that we find in nature, and it will scratch all the other substances, right? That's the whole idea. All right. Let's see. Different arrangements of the same atom can form different minerals. This is a wonderful example. And so this is really important. So if you have two things that are chemically the same, but the atoms are arranged differently, those are called polymorphs. So poly, many, morphs, different shapes, right? Polymorphs. So like diamond, very, extremely strong bonds, in carbon atoms, and then the graphite, very, very weak bonds in the carbon atoms. All right, so I just wanted to show you this before we moved on. This is in your textbook. It's page 540. Remember, you have an e-text. You can always look at that. So these are some different minerals, and these are basically the representative for this Mohs hardness scale. Okay, so there's again, this is something we're going to do in lab if you haven't already done it. The Mohs hardness scale goes from 1, which is talc, which is a very, very very weak. It's not a hard mineral at all, to the hardest mineral of them all, which of course is diamond. All right, so let's go through this. Talc is it's kind of like it's like a powder. Actually, it's actually very unhealthy. I think it has, if I remember correctly, it actually has a bunch of asbestos in it, so that's not a good thing. Gypsum is very, it's another mineral. It's actually what's used in the walls, like if you put up sheetrock, that's gypsum is the mineral that's inside it. You can scratch it with your fingernail. So here's the lesson, right? This is the basic idea. Anything that is harder, so if you take a diamond will scratch any of these, right? If I took quartz, I could not scratch a diamond with quartz, right? Quartz has a Mohs scale of 7. It's not going to scratch a diamond, but the diamond will scratch a quartz, definitely. All right, so it basically, if you're asking what will scratch, like gypsum will scratch talc, of course, because talc is, it's not hard at all. Calcite is can easily scratch gypsum. So, for example, one of the tests that we do is you take a penny, and the penny is generally more, on the Mohs scale it would be about a 3.5. That can scratch calcite, the mineral calcite. But the penny, notice that since the penny is 3.5, it will not scratch this mineral called fluorite. All right, and then there's another mineral called apatite, and then feldspar is actually a very common mineral. Feldspar and quartz really make up most of the crust of the earth, as a matter of fact. Then comes topaz, corundum, and then of course the final one is diamond. All right, so I'm going to get back to this slide. All right, so this is the next thing. So the hardness scale is, I just went over that, of course. That's the Mohs scale. It's really it's determined by the amount of how strong the bonds are. Like a diamond, there's the strongest bonds of all, and it's determined by the ionic charges that are involved in the holding the molecules together. All right, the size and the packing as well. Let's see. And so like, for example, the size, the larger molecules are not as strong. They're not as like gold. Gold is a very large molecule, and it's not very hard at all. In fact, it's a very soft metal. All right. Oh.